And good evening, AP Physics students. Hope you're ready for a little ideal gas law today, continuing our discussion of different states of matter here. So we're talking a little ideal gas law today. Now let's go back to chemistry a little bit. I'm sure you talked about the ideal gas law there. Let's discuss it here. First of all, the ideal gas law is an equation of state. That is, it doesn't matter how a gas came to be in a particular state. If it's an ideal gas, it'll follow this equation no matter what its pressure, volume, number of moles, or temperature is. Remember that an ideal gas has no attractive nor repulsive forces between the particles, doesn't form liquids, doesn't form solids. There's no potential energy between the particles, just good old particles bouncing around off of each other. Now, there's a little bit of difference between the way chemists approach the ideal gas law and the way physicists approach the ideal gas law. And you guys will figure this out really quick. It's really not too bad. Just let's kind of remember how we did it and how we might do it. And to tell you the truth, sometimes I use one equation, sometimes I use the other. Just kind of depends which is easiest. So, back in chemistry, Mr. Carefeld probably taught you that if you have an ideal gas, you can take its pressure in kilopascals and multiply that by its volume in liters, and that will equal the number of moles of gas that you have times a constant R, and then the temperature would be in Kelvin. All right, and this is the ideal gas law, and as long as you knew this law in chemistry, you could do things like, hey, pressure times volume. If the temperature is the same, the pressure and volume are inversely related to each other, and you could get Boyle's law, or pressure and temperature. You could get Guy-Lassa's law, that's Charles's law, or anyway. So anyway, that was the ideal gas law in chemistry, and it's really very similar in physics. We just use a little more basic units. Now, the numbers might get more complicated, but the units are more simplified. So for pressure, physicists just like using pascals because it's the base unit. For volume, just like when dealing with densities, we use meters cubed. Now notice, since I multiply the two, pascals times meters cubed will be the same as kilopascals times liters, because this is 1,000 times bigger, but a liter is 1,000 times smaller. So P times V, whether you use these two units or these two units, will be the same. Now, capital N, here's where we get different. This is number of particles. All right. So if you have, for instance, if you up here had 1 mole, instead of putting 1 mole down here, you'd put 6.02 times 10 to the 23rd atoms or molecules or whatever the gas is. T is still the temperature, which we always measure in kelvins, no Fahrenheit or Celsius here. And then K sub B is a new number for us. It is called Boltzmann's constant. And have no fear, it is on your table of information, so you don't even have to memorize it. But basically, Boltzmann's constant, K sub B, is equal to R, the gas constant, divided by Avogadro's number. Physicists like to use N sub A for Avogadro's, the A standing for Avogadro. So if you take 8.31 joules per degrees per Kelvin and divide it by Avogadro's number, 6.02 times 10 to the 23rd, you get Boltzmann's constant, which is 1.38 times 10 to the minus 23rd joules per Kelvin. And again, that number is on your table of information, so you don't even have to worry about memorizing it or anything like that. Okay, let's take this information and do a little problem with it, all right? Let's check out problem number 31. So problem 31 wants us to calculate the density of oxygen gas at STP. All right, so oxygen gas, of course, is O2, all right? And any amount of oxygen gas would have the same density, so why don't we pick 1 mole, right? So according to the periodic table, oxygen, or O2, 1 oxygen has a mass of 16 grams, or 0.016 grams, but it's O2 because oxygen's diatomic. So we know the mass of 1 mole of oxygen gas. Let's use the ideal gas law to calculate the volume, and then we'll have our density. So PV equals NKT. We'll take the physicist's approach here. V would be N times K times T divided by P. So at standard temperatures and pressures, if we have 1 mole, N would be 6.02 times 10 to the 23rd. Boltzmann's constant, K sub B, is 1.38 times 10 to the minus 23rd. Times the temperature, which standard temperature is 0 degrees Celsius or 273 Kelvin. Right? We always want to always use Kelvin when you're dealing with temperatures in physics. Can never go wrong with Kelvin. And then our pressure at a standard pressure is just 1 atmosphere, 101,300 pascals. So if we punch that all into our calculator, we get a volume of 0.0224 meters cubed, or 22.4 liters, which should be a number that's familiar to you from chemistry. So if I plug this in here for the volume of 1 mole of oxygen gas at STP, I get a density of 1.43 kilograms per meter cubed is the density of oxygen gas at standard temperature and pressure. All right, nice work, physics students. I am going to highlight this answer here in green today in honor of St. Patrick's Day. If you saw me at school today, I would, of course, point out to you that there was a great article in the paper about engineering a super spud, about how the technology we have to make a better potato today can actually help fight disease in potatoes. Super interesting article here about how we can use genetics and different things to make a better potato. And of course, if you would have seen me at school today, you would have seen me wearing my Irish shirt, right? Lucky to be Irish, proud to be awesome. And of course, I would also be wearing my Irish blinking sunglasses, and probably showing off the card that Raven gave me to wish me happy St. Patrick's Day. So nice work, physics students. May the luck of the Irish be with you on your ideal gas law homework. All right, take care.